The next talk is by Shiven Uppal, who will tell us about polyominoes with maximally many holes, and how would you like people to ask questions?
Sorry?
How would you like people to ask you questions?
Yeah, questions are all right. I
But
think
how, but do you want them
chat
to
box.
type them in the chat or speak, or what do you want them to do?
I think the chat box would be all right.
Okay, go ahead.
All right. Can I start?
Yep.
Hello, everyone. Today I'll be talking about how to maximize the number of holes in a polyomino. This paper was presented by Matthew Kale and Erica Roldan, and they obtained tight results on the maximum number of holes in an n-omino. I'll walk you through the exact construction and perimeter counting framework that yields asymptomatical tight upper bounds. And I would like to begin by Charles Eames' quote: "Toys aren't really as innocent as they look. Toys and games are precursors to serious ideas." All right. So Henry Ernest Dewdney, one of Britain's great math puzzle inventors, wrote Canterbury Puzzles. Polyominoes first appeared in his book even before it was defined by Golomb in 1953. Puzzle goes something like this. Once Prince Henry sat down to play chess with the French Dauphin. A fight broke out between him and Lewis, and Lewis threw all the chess pieces. Henry got furious and he hit back with the board, and the room erupted in chaos. Guards rushed in, and in the confusion, the young rivals fled France. But Puzzle says that the impact split the board into 13 strange pieces, 12 pentominoes, one tetromino, and so the puzzle was born to resemble the 64 squares into a full chessboard. Alright, so polyominoes were popularized further by Martin Gardner in his Scientific American Mathematical Games column and explored in depth by mathematician David Klarner in his research. It's a cornerstone of recreational mathematics and tiling puzzles, inspiring countless variations and challenges. In fact, tetrominoes, which are four-cell shapes, became world famous through the game Tetris, which many of you might have heard of. So, from research papers to game consoles, this idea has captured both mathematical minds and pop culture. And while polyominoes are widely studied in tiling problems, the number of holes in a polyomino is not a widely studied concept. So, the term polyominoes was first introduced by Solomon W. Golomb to describe a plane geometric figure that is formed by connecting a finite number of unit squares together along their edges. And here you can see what a polyomino looks like. Yeah. So polyominoes are simple shapes built from unit squares, and a domino has two squares, a triomino has three, and so on. If we take an n-omino, the number of holes it can contain is not obvious. Here, a hole is a completely enclosed empty space. So the function measures the largest number of such holes possible for like an arrangement of n squares. So next up, they defined a function to find the number of holes in a polyomino. And here are a few examples. So given a polyomino A, we denote the number of holes in A by h of A for n greater than equal to 1. And we define the function as max h of A, where A belongs to A of n. And the 8 omino is the smallest to have a hole, scaling the construction up to a 20 omino, which has 5 holes, and a 60 omino with a remarkable 21 holes, showing that there's a rapid growth of hole count with area. The paper also defines GM, which asks if I want exactly M holes, what's the smallest polyomino that can give me M holes? For example, a single hole first becomes possible at n equal to 7, and So this table shows g of m for m which is less than equal to 8, determined through constructive examples. Now, to understand external cases where the number of folds is maximized, Kale and Roldan had constructed special sequences of n and corresponding h number of folds. So f of nk is equal to hk, and the construction of sequences of polyominoes Rk actually achieves the maximum number of folds for that exact size nk. So the lower bound construction matches the true maximum for nk values. And function f of nk minus 1, which is equal to f hk, even if you remove one tile from Rk, which is going from nk to nk minus 1, we can still arrange the polyomino so that it has the same number of folds as hk. In other words, losing one tile doesn't necessarily cost you a whole.
There's a question in the chat.
Just a second.
So the question says, just to
So
clarify.
what do you mean? Sorry?
Go ahead.
What do you mean by enclosed at the diagonal?
Well, okay, you mentioned that earlier that the first example to have a hole is with 8 squares. But I guess I'm not completely sure what qualifies as enclosing a hole.
All right. So are you asking if this would be considered as a whole or not?
Yeah.
Yes, it will be.
Oh, okay. Thanks.
And the minimum number of squares required to have a whole is 7. All right, then. Moving on, f of nk minus 1, which is equal to hk. So even if you remove one tile from rk, which is going from nk to nk minus 1, you can still arrange it so that it has the same number of holes. And losing one tile doesn't necessarily cost you a hole. So the next case was f of nk minus 2, which is equal to hk minus 1. But if you remove 2 tiles from rk, you lose a hole somewhere. So the maximum possible number of holes drops to hk minus 1. All right, so let me walk you through the main idea of the proof. We start with an n plus 1 omino, which simply means the shape made from n plus 1 squares. And we look at the bottom row and focus on the most tile and call it L. For the base case, if there is only one tile in that row, removing it keeps the shape connected and doesn't destroy any hole. Now, for the induction step, we assume that the claim works for shorter bottom rows and try to prove it for a row of length m plus 1. Here we examine the 3 neighboring spots above L to its right and diagonally upright. There are 6 possible patterns for how these spots could be filled. In 5 of those, we can safely remove L without losing more than one hole. All right, so the tricky case is the 6th pattern, which is called C4. Here, removing L might split the shape apart. So to fix that, we remove L, but immediately add a tile in one specific spot to reconnect everything. If this covers a hole, the shape becomes one of the easier cases, again, letting us remove a tile without any trouble. And the process shortens bottom roll and lets us apply our induction hypothesis. So in the end, we can always find an anomino B whose number of holes is at least the number of holes in A minus 1. Yes, so this slide, it presents the asymptotic bounds. So if we create a polyomino with n squares, So they proved that as n grows large, f of n scales roughly as n upon 2, but with a small subtraction proportional to root of n. So these constants, C1 and C2, are found through careful geometric combinatorics. And before this paper, upper bound proved earlier for max number of folds was n by 3. Yeah, so the result comes from two directions. For the lower bound, they explicitly built polyominoes with many holes using a recursive, almost fractal pattern, copy, rotate, and remove tiles to generate new holes. And for the upper bound, they turn to geometric combinatorics, linking the ship's perimeter to the perimeters of its holes, which strictly caps how many holes you can have. Yes, so lower bound via construction. Here they build a sequence RK. They started with a single tile, then place 4 copies in a square and remove the central tile. And just a second, sorry. Sorry, yeah. Each iteration expands both the size and the number of holes in a controlled way. And the key is that this recursive construction guarantees the lower bound given here. And it's a fully constructive proof showing exactly how to make shapes that meet the lower bound. Yeah, so upper bound via perimeter argument. For the upper bound, we look at perimeter. Every hole adds at least 4 to it, while the maximum perimeter for any n omino is 2n plus square root of n. We subtract the outer boundary, and what's left must come from holes, giving us the upper bound as mentioned here. Yes, so this matches the lower bound asymptotically. So we pin down the growth rate from both directions. Alright, so the big takeaway is that polyominoes can pack holes into nearly half their area, a surprisingly dense arrangement. But this goes beyond puzzles connecting to tiling theory, combinatorial geometry, and even topology. An open question is whether similar bounds apply to 3D polycubes and other shapes, and together the constructive method and asymptotic analysis gives us a full story from small n all the way to infinity. Thank you.
Okay, thank you. Are there any other questions? Okay, yeah, I see another question from Stephen. So this is a question.
Given the upper and the lower bound for this. Just a second.
Has any work been done since that paper?
No, not really. I've been studying about this and I'm planning on writing another research paper similar to this. But I'm going to focus on deep holes. So
What are deep holes?
they'll be closed diagonally. So the minimum
so just
be 8.
just like generally like different. So like just basically different definition of connected, basically.
Could you repeat that?
So you're basically changing the definition of connected a bit.
Yeah. So in a deep hole, the minimum requirement would be having 8 and it has to be diagonally closed.
Do you just like a general graph? Like I'm not sure how you even define like an infinite, whatever. Yeah. Like given some random graph, take like a set k, take a random subgraph of size k, see how many components it splits the graph into. I guess like that's more like a random graph theory thing, though.
I'm not able to get you. Could you please type that in the chat? Sorry. Yes, I think so, but I'm not sure.
Are there any other questions? Okay, well, if not, then thank you again.